Up to this point, we've treated chemical bonds as ionic or covalent, and we've talked a lot about, say, sodium chloride having an ionic bond, and we've talked about like hydrogen forming a perfectly covalent bond, but I'm going to show you a new gradient today. This is what life is really about here. And on the ionic bond side, what you notice is that an electron gets donated to one, and then each of these separate atoms are attracted to each other by their electrostatic differences, positive and negative. And then a covalent bond over here, like two hydrogens, two oxygens, two nitrogens, they perfectly share electrons. But the truth is, 99% of life takes place right here in the polar area. If I have something like let's get out an electronegativity chart. This is going to be a chart that shows you how interested in one more electron an atom is. Okay, so obviously in the upper right corner with fluorine, let's take a darker color here. Look over here at these. These are our electronegative atoms here, all of our organic chemistry molecules, or atoms, sorry. Notice how many of those are going to be what we work with here. That's not an accident. This high electronegativity makes them want to steal electrons from others and end up bonding as a consequence. All the metals, all the transitions, all the heavy things are all in the 1 to 2 range. Not that much. The other one to pay close attention to is hydrogen. Okay, so what I'm going to do is I'm going to give you an example. Let's draw a molecule out here. Here's an H for hydrogen, C, and an N. And I think this is triple bonded and this is single bonded like this. And nitrogen has a lone pair out here, and that should cover it. Okay. But their electronegativities are 2.1. I want to say carbon is 2.5, and then nitrogen is 3.0. And what this means is that carbon is going to pull electrons over here, and they draw like a symbol like this, but don't worry about it. It just means that electrons want to kind of migrate this way. There's like a little bit of a rubber band kind of pull feel to it. And nitrogen is going to pull on carbon this way. So what you'll find is in this cloud, it's going to form kind of like an electron cloud that's kind of like this. Most of the time, electrons are going to be hovering in this general range, flying around here. They'll come out here once in a while, but then stay in this range for quite a while, and then maybe come out here one more time, and then 10 more times in this region. And so you see that density cloud mostly form electron what's a better way to say that? Mostly locate electrons closer to the nitrogen. And this kind of asymmetrical shape lends to the ability for something to act as an acid or a base, and then react and form molecules, which we'll get into in just a second. Let's have a look at an example here. Here's methanol. Okay, what a beautiful picture too. This is off openstacks.org. It's a totally free organic chemistry textbook, and I like to run from it. Okay, so over in this corner here, they're trying to show us oxygen is far more electronegative. This is going to pull electrons away from the carbon toward the oxygen, and it's going to want to hover in this range the most. Electrons still are everywhere in this cloud. They're moving at the speed of light around a distance that's like smaller than tiny of small, right? So they're everywhere. They're like literally covering every pixel of this picture hundreds of times per second, but they cover this area a few times more than anywhere else. And the thing to notice here is that their electronegativities form a difference of about 1.0. And that's important because if you have too much electronegativity, you get an ionic bond where it just tears the electron away and leaves. If you don't get enough electronegativity difference, then they'll just share a covalent bond like two nitrogens, two hydrogens, etc. But if you want a polar molecule where one region is more electronegative than the others, a difference of about 1.0 is very close to ideal. Let's look at another one. They have methyl, I can never say it, methyl lithium here. I'll pull it up. This one's a little bit more obvious. Carbon and lithium. This is a 1.5. This is still going to form a polar covalent bond, but notice here it's getting very close to just kicking this guy to the curb. Lithium, thank you very much for your electron. Peace out. F you. I'm taking it and leaving. And that is what would happen if you used fluorine. But carbon, with a difference of only 1.5, from lithium. It's just barely able to hang on to the lithium itself. So that electron cloud doesn't quite form a break here. Now, you're definitely going to see the electronegativity on the carbon side of it, which means that the carbon is acting, let's say, as an anode, right? It's the negative side of the molecule, and the lithium is your positive cathode side. So if I take something like this here, we're going to establish what's called a dipole moment. And maybe you've heard of a dipole before. But the best way to think about it is just that there's a center of mass somewhere of all the positive charges in a molecule. That would be the nuclei, right? The protons, those are the positive charges. And there's a mass of all the negative charges. So carbon and lithium, they don't exactly have the same number of positive charges. Carbon is 6, should write it over here. 6 and lithium has 3, so maybe right in here closer to the 6 is the center for all the positives. But then all the negatives, maybe I'll put it in purple here, the negative charges are way down here, and there's still, there's all 9 electrons are swirling everywhere, so there's no reason to really mark out how many there are. But you can think of it as the difference between the center of positive and the center of negative. This is your dipole moment. I'll just call it D for now. Let's see, can I pull up the last one? Do I still have it underneath? I do. So let's think about oxygen and carbon. Oxygen has 8 protons. Let's do that in blue. And our carbon has 6. So the net positive is going to be a little bit closer to the 8 than the 6. It's almost in the middle, right? They almost are the same, but a little closer to the 8. And then let's come over and look at what would be, you know what, let's put it here. Let's say here's the positive center, and the negative center is going to be more like up here. So this, you can think of it as this distance as our dipole moment here. It kind of establishes where our positive and negative is on average in a molecule. And the farther apart those are, the more interesting things are going to get. Let's use a couple examples here. Let's try sodium chloride. Everybody knows the ionic bond for salt, right? This one's classic, but let's see what we can figure out with the dipole moment here as our example. So sodium has an electronegativity of 0.9 according to this chart over here. Chlorine is all the way up at 3.0. It's one of the highest demanding atoms for an electron on the table. And it's also fairly large. Fluorine is half that size and more electronegative. That's the thirstiest of the group. Sodium, what's the sodium's element number? A10 is like number 11. So let's say he has a plus 11 charge here, and chlorine is 5 more than that, so he's like a plus 16 charge. So if the middle for salt is right here, then we'll say that the positive is kind of just a little bit to the right of that on average. So we'll say that that's our positive anchor here. And then negatively speaking, this difference is a 2.1. We know this is an ionic bond. Everything over 2 is pretty obviously ionic. But let's take a peek here at what that would be like. So the electron cloud that forms is really strong, like this. And what they find actually is that the negative is on the other side of the center of chlorine, way over here. This dipole moment, in fact, I'm underestimating this. It's more like way over here. This dipole moment has a distance of 9.0. It's one of the highest in all of chemistry. And that's really interesting because, of course, that's going to be a character of ionic bonding. If you're negative and positive centers, let's say centers of mass for lack of a better term, but remember electrons don't have mass. I'm just trying to give you some terms that you can latch onto as a basis to understand. But this distance between the average center of positivity and the average center of negativity is so wide that it only forms an ionic bond. The chlorine and the sodium aren't even really in the same electron cloud. That's why we call it ionic. But if I take something less extreme, which is almost everything, right? If I take something more like, I don't know, let's look at, yeah, I've got one for you. Let's look at methyl chloride like this. CH3Cl. Now, according to our math, carbon is element number what? 6? 1, 2, 3, 4, 5, 6. So we've got +1 here. This is all about our positives. +1, +1, and +6. And chlorine is like, no, was it element 15, something like that, like a plus 15. So the positive average is going to be about here, close to the chlorine. It's like where our positive center of mass is going to be here. Center of mass is correct for the proton side of things, yeah. But our positive center, our average positive center, right there. And the negative is going to be a little bit closer to the chlorine because, again, the chlorine, very negative. Carbon's at 2.5. That's quite a bit stronger than sodium 0.9, but it's still less than chlorine's 3.0. So this distance here, this dipole moment is measured at only 1.87. That's far more muted. So we definitely have a polar molecule. It's still kind of like this, but it's closer to something like a lumpy jelly bean than it is to be NaCl, which looked like this, and then a little like this if you look at it on an electron microscope, where they basically separate. And this is a lot closer to what you're going to be dealing with in organic chemistry, because in order for things to react and bond to each other, there's going to be a give and take, and it's going to be a lopsided bargaining agreement, but there's still going to be some kind of meeting of the minds close to the middle here. If I look at something more refined and something more famous, well, we could just look at an average. What about a carbon-benzene ring? Let's look at 6 carbons put together, and they form double bonds, so we draw it like this. But you'll notice at every corner, there's a double bond connection for 1. Yeah, that's very important, because the benzene, if I was to draw it sideways like this, there's these pi orbitals that go like this at each one that raise vertically, and they allow electrons to float in a full circle above and below this situation. And that gives it a lot of stability. But every one of these is a carbon, so carbon has its electronegativity of, was it 2.5? 2.5 everywhere. So the center of negativity is going to be right in the middle, because negative is everywhere equally, and they're all balanced out that way. And the center of positive, well, all the carbons have the same number of protons, so you're going to get that in the same spot as well here. And that is why this has a dipole moment of 0. It's a totally nonpolar molecule. And that means that it's not going to be very reactive to things that are polar. For instance, water. Let's look at water. It's got some electrons out here and a hydrogen here and a hydrogen here. Well, Jesus, I mean, look at oxygen's got 3.5 electronegativity. So you have a 2.1 for hydrogen and a 3.5 for oxygen. It's going to pull electrons this way, and we draw it like this. It's going to pull electrons this way. So you're going to have this bent electron cloud like this, with the dipole moment far being this direction from center. And the only thing that keeps this really together is oxygen has a lot more positive charges than hydrogen, right? So the center of mass is mostly going to be at about this height, and the negative is going to be at about this height. So you get a dipole moment here. And it's of about 1.85, just very similar to the methyl chloride I just showed you. There's an obvious polar side to it. There's a negative side to this cloud, and a positive here and a positive here when you look at it on an electron microscope. When I bring that kind of a polar molecule into the world of benzene, this carbon ring here, he has no awareness of this molecule's interest in reacting. Benzene's like, I don't care. I'm a neutral body. I'm Switzerland, baby. And that is why exactly we need polar solvents, nonpolar solvents. That's exactly why certain things mix and other things don't, is this exact principle here. So let's move into the next video and see how we can play with this.